Alright, so hi guys. This lecture is going to be on a sort of paradigm that's called reinforcement learning. And reinforcement learning is kind of like one of the highlight intersections between the fields of neuroscience and computer science. And it's led to some pretty awesome research and real world advancements over the past couple of years. And it's sort of the perfect example of how studying one of these subjects can lead to advancements in the other and vice versa. And so that's what we're going to be talking about today. And before I get started, just credits for all the material in this lecture is actually from slides from a class that was given at the University College of London, and the professor is David Silver. David Silver is a researcher at the company known as DeepMind, and he's been responsible for a lot of the reinforcement learning advancements that have come out of the company over the past couple of years. And so, if you're interested in learning more about reinforcement learning, we're probably going to do more lectures on this topic in the future. But if you want to explore this on your own, you can just search up like UCL reinforcement learning course, and a lot of interesting. There's like a lot. All the YouTube videos are online, and lecture slides as well. Okay, so now let's get started. So reinforcement learning is basically training an agent or a program to maximize its reward that's acquired by interacting with some environment, right? And so the sort of problem specification that I just gave is very vague, and it can mean a lot of different things. But basically, uh, reinforcement learning is different from traditional types of machine learning. In traditional types of machine learning, which we sort of touched on last lecture with neural networks, we're sort of getting our neural network to learn some function, right? And this can be like predicting whether an image has, like an fMRI image, corresponds to someone with Alzheimer's or not, right? So we have some inputs and some outputs, and we basically show a bunch of different pairs from this data set that we know are correct. And after repetitive training, we can essentially, the computer essentially learns the function. That's what we were talking about before. But here, we do no such thing. We don't give correct examples to our computer to learn. Instead, our computer learns from experience, right? It interacts with its environment many times, and and it sort of learns how to interact with whatever environment we put it in the best way possible to acquire the greatest amount of reward from that environment. Right? So, as stated on this slide, the agent's job is to maximize the cumulative reward it receives over its run. And so that sort of lends to that sort of, if you, so this is very vague, right? It's very general. um, and reinforcement learning has been applied to a wide variety of tasks. And the sort of so the this is called the reward hypothesis, which basically says that all goals can be described as simply the maximization of some cumulative reward. So there are some like philosophical questions that are raised by this, right? Maybe not all goals are can be described. Like if you ask someone what's the meaning of life, uh, it's usually not like, oh, I want to increase this number, whatever that number may be, right? So human goals are somewhat more complex, I think, or it's not easy to just assign a number, at least for us that we know of. But for the task that we would like computers to learn, um, we basically come up with some reward that specifies what um, what they should do, right? And then they essentially learn how to maximize that reward. Okay. Um, Actually, I'm gonna go to the next slide first before we watch this video. But some examples of rewards are, let's say we were teaching a helicopter how to perform a bunch of stunts, right? Like a remote control helicopter. Then every time the helicopter performs a stunt, we can reward it, some number of points. And then if it crashes, then we subtract a number of points. And basically, the subtraction is um, a punishment, right? Whereas a positive reward is a reward. Um, some other examples, like if you're training a reinforcement learning program to manage an investment portfolio, then you could say for every dollar in the that ends up being in the account, that's a positive reward. And if you end up losing money, then that would be a negative reward. Actually, you don't need the second part. Just if your goal is to maximize the reward, then the agent's goal would be to maximize the amount of money in the bank. So there we only need a positive reward. We don't need any sort of punishment, right? And this one, which we're going to go back to on the last slide, if you're maybe training a program to play Atari games, then you can link the reward to the game score. And so the agent is then incentivized to play the game as well as possible, leading to a positive reward. Or if it decreases its score, then a negative reward. Uh, and so this is actually a video from Google DeepMind, which is the same organization that David Silver works for, right? And so this was in 2016. It's sort of like a breakthrough in reinforcement learning and in the field of machine learning, where the team basically trained a program to learn how to play a bunch of Atari games from scratch. And so the key thing to realize here, before I play the video, here, I'll just play it. The key thing to realize is that the computer was not programmed to like move towards the ball, right? All it was given was the pixels on the screen, and then it was given the action space of moving the joystick, from left to right. And there were some other like small things that you could do with the joystick, but they're not very important. Um, and so it's sort of like it's learning from a blank slate, right? It knows absolutely nothing, and it's figuring all this out by itself, with the sole goal of maximizing the reward, which is linked to its score. And you can see, it just got pretty good in the last episode, but here it actually learns the strategy to hit the ball behind the bricks here to decrease the chance that the ball goes past it. And so this is like really amazing. And it learned all of this just with the goal of maximizing the score and then seeing the pixels on the screen. So this is like a huge sort of a breakthrough success in reinforcement learning. Um, and so this is sort of an example of what you can do. Right? So basically the formalization of a reinforcement learning problem is that you have some agent, which is depicted here as this brain icon, like it's some intelligent agent. That we use the word agent to like say program, right? our our agent is interacting with some environment, and here the earth is the environment. And it's interacting solely through a set of actions. um, so it can take actions that somehow affect the environment that it's in. And on every new time step of our run, the environment will return to us a new observation. So we somehow get some sort of representation from the environment back into our agent. And then based on that new observation, our agent will then take another action, right? And then intermittently or continuously, the environment is always giving rewards to the agent. Um, it doesn't have to at every time step, but it could. And that just depends on what the agent is doing in the environment, right? If the agent achieves the goal, then the environment could, give us a reward. Um, and just to be clear, all of this occurs in sort of like a time sensitive space where, like, every time step, our agent takes an action and then receives an observation. And this just keeps happening until like our episode gets terminated. Um, so in a lot of at least the basic reinforcement learning problems, the state or the observation that we get from the environment has to satisfy this thing that we call the Markov property. And the Markov property basically says that given the current state, we can ignore all the previous states. And so translating that, I mean, this is just like the formal expression of that, but basically this says that the probability of the next state given the current state is equal to the probability of the next state given all the states, starting from S1, which was our first state, all the way to the last state. So what this means is, translated succinctly, the future is independent of the past given the present, right? Basically what that means is that all the information that we need to make future decisions in our environment is completely encapsulated by the state that we currently have. And we don't have to make use of any information from previous states. So this notion of state is sort of vague still, but the state can be anything, right? As you'll see, like for the Atari example that I showed on the last slide, the state was just the grid of pixels that were shown on the screen, right? Um, for maybe like the helicopter example where you're trying to get a helicopter to maneuver stunts, the state could be a bunch of positional information about the helicopter, like the velocity of the helicopter, wind direction, the direction, or velocity is direction, but uh, a lot of different positional information about the helicopter. And so the state can be anything. But what the Markov property says is that given some state, that state is all we need to predict the rest of like the next state. And so basically, a way to guarantee that you satisfy the Markov property is to give whatever internal representation you have in your environment to the agent directly, right? So if the agent sees every single thing that's happening in your environment, then that is that automatically satisfies the Markov decision process, the Markov property. And if this is the case, then we formally call this sort of reinforcement learning problem as a Markov decision process. Don't worry if this doesn't make too much sense, because if we delve into this topic of reinforcement learning further, we're going to spend a bunch more time talking about the Markov property and Markov decision processes. But basically, all this slide is saying is that a way to guarantee that this property is satisfied is to just give the whole representation, like every single possible little thing that our environment is, like every single piece of little information that corresponds to our environment, and then feed that to our agent. And the agent is some algorithm that makes sense of all of that. Granted, this is kind of hard, especially in a lot of real world scenarios where the representation, like representing every little single thing of our environment, can be difficult, right? You don't always know everything in your environment, and so there's sort of like a sub problem called like partially observable Markov decision process, where you don't know everything, and there are also algorithms that we have that deal with those sort of situations as well. But if you go on to like study reinforcement learning, a lot of introductory courses, like the majority of the introductory courses, will first focus on solving this problem, which is and once you understand how to solve this problem, it becomes fairly easy to like generalize that to partially observable environments as well. But yeah, this is just something to note. Okay, and so now we've been sort of vague in what is exactly the brain icon that on the last slide. And so we're going to talk about the different components that could be in a reinforcement learning agent or reinforcement learning program. There's three main sort of components. One is the policy, one is the value function, and one is the agent's internal representation or model of the world. And so we're going to talk about each of these on the next few slides. Okay, so the policy basically defines an agent's behavior, right? And so we usually define this as we use the letter pi for policy, and given some state, it it's the policies can either be deterministic or stochastic. And what this means is, for deterministic, um, given some state, it always maps to some action, right? It's always the same. Whereas in stochastic policies, we define a probability distribution where, for some state, we assign various probabilities to each of the actions in our action space. And then when we're actually acting in our environment, we'll just randomly sample from all of these probabilities. So don't worry if that didn't really make sense. The key thing to note is that, a policy maps a state a state to an action, right? So when you're in your environment and you get some observation, then the function that basically tells you what action should you take next, that's the policy, right? It's a function that inputs the state and then outputs either a single action to take or a probability distribution of different actions, and what probability you should pick them with. Um, so that's what a policy is. And so let's say this was sort of our reinforcement learning toy problem, right? Where the goal is to train an agent to essentially start from here and then navigate to this place in the maze. So a policy, you could just represent this with the sort of like array or 2D matrix or something, where in every state, these are all the possible states in our environment here. You just draw the arrow that you should move in order to reach the goal as quickly as possible, right? Here you can imagine like the reward would be maybe like -1 for each step, and then when you get to the goal, you get like maybe like plus 100. And so you can imagine that, if that is the case, then since you're getting a negative reward on each time step, the agent is incentivized to move through the maze as quickly as possible, right? So this would end up being the optimal policy, where if you started off here, you would go to this block, and if you got to this block, you'd go here, and so on and so on and so on. And so this image basically represents a good policy for this problem, right? Um, and at this point, you might be asking, okay, that's cool and all, but how do we actually determine this policy? So that is a sort of complicated question. There's for toy problems like this, there are ways that you can just, after repeated runs of your agent on this environment, it will basically come up with this whole policy where for each and every possible state in your environment, you have a corresponding action, right? There are algorithms for that, and we may get to those in future lectures. But in real world scenarios, when you have really high dimensional like action spaces, or when you have like a lot of states, right? There's not always going to be like a right answer. I mean, it's really hard to determine what that answer is for every single possible state. If you have, you know, in the game of chess, for example, uh, there are over like 10 to the, there are like 10 to, I think, I don't know, I think like 40 or 60, 10 to the power of 60 different board configurations, right? I think it might be 120 actually. But f- in order to do something like that, there's just not enough compute power to take every single state, um, and then get a corresponding action. So for those types of problems where there's a really large like number of states, we use different sort of techniques to determine the optimal policy, and we may get to those in future lectures. Okay, so now that we discussed the policy, we can also discuss something called the value function. So the value function is basically, given a state, you predict the what the cumulative future reward will be. And so given this value function, it basically tells you how good is the state that you are currently in. So this is sort of like the mathematical formalization of that, where this is, the formal definition of this is the expected return of the reward, given this state. And so that's going to be the current reward plus um, the reward on the next time step multiplied by some discount factor, and then the reward on the next time step after that multiplied by the discount factor squared, and so on and so on. And this discount factor here is basically going to be a number between 0 and 1. And what this does, it essentially incentivizes, it prioritizes rewards that are sooner rather than later, right? You can imagine that if this is 0.99, then this would be 0.99 times RT plus 2, and this would be 0.99 squared, which would be less than 0.99 RT plus 3, and so on. And it would keep, this is like decaying. So you're basically prioritizing rewards that come sooner in your life than later. And you can basically, like, if you set this to 1, then it basically treats all rewards as equal. And so you don't really care about the current reward any more so than you do for future rewards. But if you set it to 0, then you only care about the next reward, and you don't care at all about future like rewards down the line. And so this is a very important thing to understand, because a lot of times you may actually have to go like one step back to go two steps forward, right? Like there are many instances where you have to take some action that decreases your reward on the current time step, but it increases the reward in future instances, right? So you have to keep this in mind. And so given this value function, you can basically just, in every state, once you find yourself in some state, you can figure out what are all the possible subsequent states, and then just choose the state that has the highest value function, right? So you technically don't even need a policy here. All we need to do is just greedily choose which one of the future states we should go to, and then just choose the action that corresponds to that state to getting for us to get to that state. And so for the same grid world problem that we were talking about earlier, this could be like a possible value function. And basically what this means is we can see that the reward here is like greater than the reward here, and it's greater than the reward here, right? So if we were here, then the optimal action would be the action that gets us to this block. And then the optimal action here would be the action that gets us to this block, and so on. And you just keep following this until you get to your goal. So at every time step, you just greedily choose the state that gets to you the greatest value. And so lastly, we have a model. And the model is basically a representation of your environment, right? It's internal to the agent, but it's sort of the agent's internal view of the world outside of it. And so there can be two components to the model. One is predicting a state, given a state and an action pair. So given the state that you're currently in and the action that you want to take, predict what is the next state going to be. So that's this portion. And then R here is basically predicting the reward. So if you take the current state and the current action, like whatever action that may be, what is the expected reward that you're going to get? And so for a grid world problem here, you can imagine that this could be a sort of model of our world, where here the P thing that we discussed earlier, which represents the probability of the next state, here that's sort of represented in the boxes that are adjacent, right? So for this block here, the adjacent blocks are here and here. So this sort of represents P, our transition model. Like what states can we get to given the current state? And the numbers inside all of these boxes represent the immediate reward that our agent would receive if it goes there, right? For all of these, it's -1 because that's sort of how the programmer in this scenario specified. We talked about how setting it to -1 would incentivize the program to go as quickly as possible, and so that's why it's -1. And so this is basically a model. And just to note, the model may be imperfect, right? It's just some sort of internal representation that the agent has, and that's not guaranteed to model the actual environment as accurately as possible. So it very well may be wrong. Okay, and so now putting everything that we just talked about together, we can see that there are like three main components to RL agents, and most of current day research falls under, somewhere on this Venn diagram. The key thing to note is that you can have an RL agent without a model, but you need to have either a policy or a value function, right? Because the reason being is that you need some way to actually take actions for your reinforcement learning agent, right? And the two ways to actually choose actions are value function, where given the value functions of all the surrounding states, you just go to the state that leads to the greatest reward that has the highest value, or the policy, which sort of sidesteps the idea of getting this value function and then goes directly to, okay, given a state, what action should I take, right? So you need either one of these two things. A model can be helpful, but you don't need a model, but you need either a policy or a value function. And so just before we go, just to reiterate, there is a strong connection between the sort of algorithms or the ideas that we talked about today. Today we basically sort of formulated the problem. We didn't really talk about the algorithms that actually help us acquire the value function or the policy function. But there is a strong connection between reinforcement learning in the context of computer science and in neuroscience. And that's basically because reinforcement learning is the study of decision making, right? We are training agents to make decisions in some environment. And there's actually a lot of evidence that reinforcement learning is kind of is implemented in our own brains and a lot of other animal brains, using the neurotransmitter dopamine. And dopamine is basically the pleasure neurotransmitter, right? And for it gets sort of released when we engage in behavior, various types of behavior, from like social media to eating to sexual reproduction. And it's also released by a lot of drugs, and it leads to a lot of pleasure. And animals are sort of hardwired to perform the actions to maximize that amount of pleasure. And so if you think about it that way, animals are conducting reinforcement learning all the time as well. And so in future lectures, we may talk about this connection in greater depth. Thanks for watching.